We looked at creatinine clearance, we looked at pharmacology and PK/PD of aminoglycosides. We also looked at traditional and extended interval empiric dosing of aminoglycosides. Now, the last learning objective is, given a patient with a gram-negative infection, select an individualized aminoglycoside dose and frequency based on serum aminoglycoside levels. Aminoglycosides follow first-order kinetics, also known as linear kinetics. And the reason this is called linear kinetics is because if you plot the natural log of aminoglycoside plasma concentration on the vertical axis and time on the horizontal axis, then you can actually get a linear relationship between two levels. This is assuming that the two levels are after the infusion and after the distribution phase. When you first start the infusion, the levels go up very quickly till the infusion is stopped. At this point, the concentration is at peak level, followed by a rapid drop in concentration for two reasons. One, the kidney starts to clear the drug, and two, the drug is also distributing into tissue throughout the body. This is known as the distribution phase. Once the distribution phase is over, meaning that all tissue is filled with the drug, then the levels drop at a slow rate because it is now only due to clearance by the kidneys. And it's during this phase that we would like to get levels to calculate the slope of the line, which would give us the elimination constant, or negative K. You can use the famous equation C equals C naught times e to the negative KT. And basically means that your final concentration equals your initial concentration times e to the negative KT. And the T is the time between the initial concentration and the final concentration. Another way of saying this is that C2 equals C1 times e to the negative KT. It's just a matter of how you label it. You can adjust the dose based on the measured peak and trough, or the two levels that you have, by calculating a patient-specific K. And the way that you calculate the patient-specific K is by rearranging that equation to solve for K. So imagine that your first level is here after the distribution phase, and we're going to get that level at time 1, and then you get the second concentration later during that same dosing interval, and that will be at time 2, and then the time that it takes between the two concentration would be the delta T. Or in other words, is T2 minus T1 will be delta T. And that is the T that goes into this equation. Now keep in mind that the first level, C1, it has to be at least 30 minutes after the end of infusion, because at the end of infusion you have your actual peak. But if you actually measure the peak at the end of your infusion, then you end up with the wrong slope. Because, for example, if you use this as your peak, and then with the C2 concentration, and you calculate the slope, you can see that the slope is very different. So it would falsely give the notion that the body is clearing the aminoglycoside very quickly. Similarly, if you measure the peak and use it with C1, you're going to get a very steep slope, which would give you a false notion that the body is clearing aminoglycoside very quickly, which is not true. So it's very important to get your levels at least 30 minutes after the end of infusion to make sure that it's outside of the distribution phase. Now, what's different about this K as opposed to the K that we calculated previously is that previously we used population data to estimate the K, so that's not very specific to the patient. But now, because we have two levels from the patient, this K is specific to the patient. So we call this individualized pharmacokinetics as opposed to population-based kinetics. Of course, if C1 and C2 are not true peak and trough, you can actually extrapolate. So you can say the equation is peak equals trough times e to the KT, or another way of saying it is trough equals peak times e to the negative KT. Again, these are all the same equation. It's just a matter of rearranging them to get what you're looking for. And of course, what you do with the K is to get the individualized volume of distribution. So the volume of distribution that we calculated previously was an estimate. But this time, since we have a specific K from the patient, we can actually calculate the actual volume of distribution in the patient. And what we do with the next is to calculate tau again. So now instead of the estimated K, we use the actual K that we calculated in the patient. So get the new tau. And then using the new tau and using the individualized K and the individualized volume of distribution, now we come up with a dose that's very accurate in the patient. Once we get the dose and tau, then we can actually verify to see if it's gonna give us, if the new dose and frequency is gonna give us the peak and trough that we want. So we can actually use this to estimate what peak we can expect from this dose and frequency. So you plug it in and it will tell you what the peak is, and then you use this peak here to see what trough it would give you. And that's how you verify to see if the dose and frequency that you're about to recommend is actually gonna give you to the goal peak and trough. We will do exercises in class to do some calculations. This concludes this presentation.